Decision tree actually consists of two parts. In the first part, we construct decision tree using training data. And in the second part, actually we cut some branches of decision tree and make the tree small. And that is called a decision tree pruning. So now we're going to talk about decision tree pruning here. Before we move on to decision tree pruning, I'm going to talk about the training data, test data, and the validation data first. So if you look at this picture here, let's say we have one original data set, and this data is divided into training data and test data. And this training data is used to create machine learning models in this case decision tree. Okay, so we use training data to to build a machine learning model, and then once the model is created, we use test data to evaluate the performance of the model. Okay. So that's the difference between training data and test data. Okay, these are disjoint to each other. And in some other cases, this training data is divided into training data and validation data. Okay, so in this case, again, we use training data to create a machine learning model. Again, in this case, decision tree. So once the model is created, you want to improve the model. Okay. So when you improve the model, you can improve the model by tuning parameters like this, or you generate multiple models and choose one of them. Okay. So you want to tune parameters, or you want to select different models. So to do that, you use validation data, okay, and evaluate each of these models. Okay, that's the purpose of using validation set. So finally, you have by using validation set, you evaluate the different model, and you have final winner. Okay, final model. And that final model is now evaluated by using this test data. Okay, so that's the difference between the training data, test data, and validation data. So in machine learning, we create the model, and actually the goal of creating model is to predict the test data correctly. So test data is, again, this is the data of future. This is the data not used in training. Okay, so this is our goal, to predict test data correctly. So original data is divided into training data and test data. So we use training data to build, or sometimes you say train, to build a model or to train the model. Okay, that's the purpose of training data. And then once the model is created, we use test data to test it. Okay. And sometimes this training data is divided into training data and validation data, and this validation data is used for tuning the parameters or selecting different models. Okay, that's the purpose of using validation data. So this chapter is about decision tree pruning. And then why do we prune decision trees in the first place? So if you prune decision trees, you cut branches and you make trees smaller. So you make these decision trees smaller. Then by making decision trees smaller, actually you can avoid overfitting problem. So then what is overfitting problem? So overfitting is very famous, well-known problem in machine learning in general. So actually, I'm going to cover this overfitting issue in a separate chapter. But here, for now, I'm going to give you a very short introduction of overfitting. So this is the definition of overfitting. Suppose we have two classifier H and H prime. Classifier can be any classification algorithm like decision tree or neural net or deep learning, SVM, whatever, okay? So let's say we have two classification algorithm H and H prime. Then let's say for training data, okay, for training data, the error of H is less than the error of H prime. So that means the performance of H is better than the performance of H prime using training data, right? So in training data, H shows better performance than H prime. However, in test data, okay, error of H is larger than the error of H prime. That means performance of H prime is better than performance of H in test data, okay? So if you look at the previous slide, okay, what really matters is the accuracy of test data. So in previous slide, I said the goal of machine learning model is to predict test data correctly. So this is really important, okay? So in this case, classifier H, this one shows better performance in training data, but shows poor performance in test data, right? So in this case, we say classifier H overfits, okay? So that's the definition of overfitting. So in this case, we say classifier H overfits the data, okay? If there exists another classifier H prime with great error on training data, but less error than less error over test data, okay? Then it's classifier H. We say classifier is overfitting, okay? So as I said, this overfitting is very famous and a serious problem for almost every machine learning method. So it turns out that these complex decision trees actually degrade the performance, and the simple decision tree is actually better than the complex ones. So by cutting branches, we make decision trees simpler, and it turns out this simpler decision tree is better than complex ones. So let's take a look at this picture here. This one shows the size of tree, actually the number of node, okay? And this one is the accuracy of the decision tree. And this solid line is the accuracy of training data, and this dotted line is the accuracy of test data. So as the decision tree becomes more complex, okay, going this way, okay, you see the accuracy of training data goes up, keeps increasing, right? It makes sense because we build a decision tree, okay, to reduce training data. And then but again, what really matters is the test data, accuracy of test data. So if you look at the accuracy of test data, so accuracy goes up here, okay, and then after this, actually it goes down, okay. So as tree becomes more complex, in the beginning, the accuracy of test data goes up, which is good, but after around this point, it actually goes down, okay. So that's the problem. So if tree is too complex like this, okay, the accuracy of test data is, let's say, around 70. But let's say the size of tree is around 10 or 15, the accuracy of test data is around 75, which is better than this, right? So you can see here, complex data actually degrade the performance, and complex data is worse than the simple decision tree like this. Okay, so this here is called overfitting. This decision tree is overfitting. Okay. So the goal of overfitting in decision tree, the goal of decision tree pruning is to cut some branches decision tree and make decision tree smaller, simpler. Okay. Let's say trees may grow to include irrelevant attribute. Now you may wonder why this complex large decision tree actually degrade the performance. There are a couple of reasons. The first reason is, think about it. If you increase the size of decision tree, that means you keep adding attribute node, right? When you build decision tree, you keep adding attribute node. So as the tree, as the trees grows, you keep adding the attribute. But in the beginning, the attributes are pretty good. If you remember, when you select attribute, you select attribute based on information gain or gain ratio. Okay, so in the beginning, the attribute you select are very high quality. Okay, very pure attribute. But later on, near this side, all the remaining attributes are pretty much poor, uncertain attributes. So around this stage, you have to add impure, irrelevant attributes. Okay, that's one reason. If tree is too complex, you end up adding impure, irrelevant, sometimes useless attribute to the decision tree, okay, that actually degraded the performance of decision tree. Second reason is, okay, so when you select this attribute, when you select attribute, again, you select attribute based on information gain or gain ratio. Okay, these are computed based on data, okay? And many data actually are noisy, okay? So later on this stage, you select attribute based on noisy data, okay? That's another problem. So if your tree grows like here, and it grows very complex like this, actually you add the irrelevant or useless attribute to the tree, and the data here are pretty much noisy. Okay, so you make decision based on noisy examples. Okay, that's another reason why these complex trees actually degrade performance. Okay, so far I explained that the small decision tree is better than large decision tree. In other words, a small model is better than complex ones. So actually this concept or this principle is quite general and universal actually. And it is called Occam's razor. So this was first proposed by this person, William Occam, back in 1300 something. It says entities should not be multiplied without necessity. If you paraphrase it, it says the simplest solution is most likely the right one. So what it means here is, suppose you have a multiple solution or hypothesis or whatever, okay? Then also suppose each of these solution has quite similar performance or same performance, right? Then you go with the simplest solution. You choose the most simple solution, okay? And then that solution is most likely the best one in the future. So that's Occam's razor. So again, as I said, that this principle, this concept, okay, this concept is true in decision tree. This concept is true in machine learning in general, okay, and this is also true in our daily life, okay. So, for example, in machine learning, you have multiple machine learning algorithm, okay, and let's say each of these shows pretty much similar performance. Then you go with the simplest algorithm, simplest model, okay. Then probably that simplest model is the best in the future. Same thing in our daily life. You have multiple choice of solutions, okay, and assuming each solution has pretty similar performance, okay, or prediction, whatever, then you choose the simplest solution, okay, then probably that solution is the best in the future, okay. That's Occam's razor. This is very famous philosophical terminology. This is similar. Everything should be made as simple as possible, but not simpler. So in machine learning area, so in the context of machine learning or science in general, if you have multiple hypotheses, then you prefer simple hypothesis over complex one. Okay. So when you are presented with competing multiple hypotheses, then you go with solution with the fewest assumptions. So fewest assumption means the simplest solution. Okay, so you are presented with multiple competing hypotheses. You choose the simplest solution, and then that solution is most likely to be the best one in the future. So we avoid overfitting problem in decision tree by pruning. So after pruning is done, the decision tree becomes smaller. So the classification accuracy of the smaller decision tree on test data may go up, okay, may increase. So as I said, because of the Occam's razor, a smaller decision tree shows better performance in on test data in the future. This picture shows an example of tree pruning. So let's say in the beginning you construct entire decision tree like this, okay, and then in phase 2 in tree pruning, let's say you cut branches along this curve like this, okay, then as a result you have a decision tree like this, right, a smaller version of decision tree. So because now it's smaller, and this decision tree is less likely to suffer from overfitting problem. Okay, now let's actually prune decision trees. There are two kinds of pruning method. The first one is a pre-pruning method, and the second one is a post-pruning. So in pre-pruning method, actually pruning is done when you grow decision trees. Specifically, pruning is done when you insert your attribute to the decision tree. So what happens is, so you select an attribute by using information gain or gain ratio, and then you're gonna insert the attribute to the decision tree, right? But in pre-pruning, before you add your attribute to decision tree, there are some conditions where you do not add attribute and stop there. So you simply stop there and do not add attribute and just ignore the attribute. There are some conditions, okay? So there are a couple of conditions listed here. The first condition is, so before you add an attribute to the tree, you run a chi-square test. So chi-square test is a very famous statistical test which actually tests two variables are independent to each other. So in a chi-square test, you select an attribute, right? And you run chi-square test between the attribute you selected and the class label attribute, target attribute. So you run chi-square test, and if these two variables, these two attributes are independent, then the attribute you selected is just meaningless, okay? It's independent to a class label, means it's not important, it is meaningless, right? So in this case, you simply ignore the attribute and you stop there, okay? You do not add the attribute to decision tree. Second case is, so you select an attribute and the number of data in the attribute is very small, like I don't know, maybe just a few, 2 or 3 or something. Then again you stop there, okay, because the number of data is too small. It is impossible to make a reasonable decision out of very few data. So you stop there and just ignore the attribute. And third case is, okay, again you select an attribute and let's say almost every data in the attribute belongs to one class value. So for example, almost every data in that particular attribute, its class value is 99% of them is one class value like yes or something, okay? So 99% of them is yes. Then in that case, instead of adding attribute, you add class label to the decision tree, which is much easier and simple, okay? So these are the basic method of pre-pruning here. Second pruning method is post-pruning. So in post-pruning, you grow your decision tree in full, okay, all the way to the end. And then after that, you cut some branches of the decision tree. So that's how the post-pruning works. There are a couple of methods in post-pruning. We're going to cover these two, reduced error pruning and sub-tree replacement in this chapter. So in reduced error pruning, what we do is you split the training data into training data plus validation data, okay? So and then using training data, just like we did, using training data, you construct decision tree, okay? So now decision tree is constructed. Then for each branch of the decision tree, you make decision, okay? You make decision whether you're gonna cut this branch or not, okay? Let me repeat. You split training data into training data and validation data, okay? And then again, using training data, you build decision tree in full, complete decision tree. And then for each branch, okay, for each branch of the decision tree you created, you make a decision, okay? You're gonna decide whether you want to cut this branch or not, okay? Then the question is, how do you make decision? How do you know you're gonna cut this branch or not? Okay, the way it works in reduced error pruning is the following. So So you have original decision tree, okay? You have original decision tree, and then using now validation data, okay? I told you you have training data and validation data. So using validation data, you test the performance of original decision tree, okay? And then you cut a certain branch, whatever it is, you cut a certain branch of original decision tree, okay? Then you have pruned the decision tree, right? So now using validation data, you test the performance of pruned decision tree, okay? So you now after that you compare the performance between these two decision tree, the original decision tree and the from the decision tree, you compare the performance of these two using validation data set. Okay, so if the performance of pruned decision tree is better than original one, okay, using validation data, then you go ahead and cut the branch. Okay, that's how it works in reduced error pruning. And you repeat this process for every branch of original decision tree. That's the basic idea of reduced error pruning. So again, you're gonna cover this thing later on. Okay, so move on. Second, the post pruning method is called sub replacement. So again, you create original decision tree. Okay, you construct decision tree in full. Okay, all the way to the end. Okay, and then again for each branch, you kind of estimate of error, estimate of the error, estimate of error when you replace this branch by a class label. Let me repeat. So you create a decision tree in full, okay, and then for each branch of original decision tree, you assume this branch is replaced by a class label, okay. Then you estimate the size of error by replacing this branch by a label, okay? You somehow estimate the error, okay? So if the estimation of error is lower than the current error, then you go ahead and replace the current branch by a class label, okay? So that's the basic idea of subtree replacement. Again, I'm going to talk about this later on. So anyway, there are two pruning methods, pre-pruning, post-pruning. And usually post-pruning shows a better performance. And the main reason is in pre-pruning, sometimes it stops too early, and so the decision tree becomes too small, okay? So because of that, the post-pruning is usually known to show better performance. In pre-pruning of decision tree, we're going to focus on chi-square test pruning. So chi-square test is a statistical significance test. So the goal of chi-square test is down here, is to test whether two variables are independent to each other. So the idea is this: you select an attribute, right? And you want to add the attribute to the decision tree, right? But before you do that, you run a chi-square test between the attribute you selected and the class label attribute, target attribute, right? So, so after the test, let's say the attribute you selected turns out to be independent to the class label, then you don't have to add the attribute to decision tree. It doesn't make sense, right? The attribute you select has nothing to do with class label, okay? So in that case, you stop adding the decision tree. You stop there, right? So that's the basic idea. So ID 3, the decision tree, use chi-square test in addition to information gain or gain ratio. So as I said, when you select attribute, you select attribute based on information gain or gain ratio, right? But before you add the attribute to decision tree, you run chi-square test, okay, and then test whether the attribute you selected is independent or not to the target attribute. Okay, so if the attribute is independent to target attribute, then you stop there. Okay, that's the basic idea of pre-pruning with the chi-square test. Okay, this slide shows the basic concept of chi-square test. So let's say we have two variables, richness and happiness, and we're going to test whether these two variables are independent or not using chi-square test. So richness has rich and poor, and happiness has happy, unhappy. Suppose we have 100 people, okay, and these numbers are the real count, the actual number of people. So we have 20 happy rich people, and then we have 60 unhappy poor people, etc. Okay. Okay, so these are the real number of people, a real count. Okay, then now suppose these two variables are completely independent. That means this richness has nothing to do with the happiness, okay, or vice versa, okay. So in that case, we are able to compute the estimate value of each estimate count of each value here, okay. So actually these are the estimate count of values, assuming these two variables are independent, okay. So let's go over this. So we have, let's say we have 20 people, right? We have 20 rich people, and if you look at the number of happy people, unhappy people, you have 40 happy people and 60 unhappy people. So suppose if this richness and happiness are independent, then out of 20 rich people, okay, 40% of them should be happy and 60% of them should be unhappy, okay, assuming these two variables are independent, right? So in the same thing here, we have 40 happy people, okay, and again, assuming these two are completely independent, then out of 40 happy people, 20% of them should be rich and 80% of them should be poor, okay? So that's the estimate count, assuming these two variables are independent, okay? So actually these number here are the estimated count of each value here, okay? So the basic idea of chi-square test is, so these are actual count and these are the estimated count or expected count. So the more different between these two values are, okay, the more different these values are, the more likely that these two variables are dependent, okay? Let me repeat. So you see numbers, these are actual real count and these are expected count, okay? So there are a lot of difference between these. If there are a lot of difference between these numbers, so these are different from these, and this is different from this. If there are a lot of difference between these numbers, that means there is strong relationship between these two variables. Okay. So that's the basic idea of chi-square test. So by the way, this is the way we compute the expected value of each value, expected count. It should say expected count of this value. Okay. So in this case, expected count of rich happy can be computed by 20 times 40 divided by 100. And for the case of poor unhappy, you can compute the estimated expected count by computing 80 times 60 divided by 100. So it's mentioned right here. So you have expected values, expected count, and you have actual count. Now, in chi-square test, this is chi-square, the formula of chi-square value. Okay, so chi-square value is expected value minus expected count minus actual count, and the square of them is divided by expected count. Okay, and you do summation for every combination of I, J. Okay, so it works like this. For every cell here, for every count here, you calculate the difference between these, okay, and square them, and compute difference between these two, okay, and square them, and compute difference between these two and square them. Okay, so you divided by expected value of this. So each value is divided by this, like this, and finally do summation for every combination ij. That's chi-square. So for this particular case, this one here, rich, happy, expected count is 8, actual count is 20. Okay. Here, expected count is 12, and the actual count is 0, right here. Okay. And here, expected count is 32, and the actual count is 20, right here. And the expected 48, and the actual is 60. Okay. And again, for each term is divided by expected count, like this, 12 expected count, like this. And you do summation. This is the final chi-square value. Then you look at the chi-square table with the confidence level, and you can decide whether this variable, richness, happiness, is dependent or not. Okay, this is the basic introduction of chi-square. So that way you can compute, decide whether two variables are independent or not. So in a previous slide, we have seen the basic concept of chi-square test. In this slide, we're going to take a look at how the chi-square test is used in pre-pruning. So let's say you select an attribute x, okay, and you're going to add x to the decision tree here. And because we are using the pre-pruning, you have to decide whether you want to add this or not, right? So we use chi-square for that. So let's say x has two values, tf, okay, x has two values, and also suppose the class level has two values, p, n, okay, so both are binary. X is binary, tf, and class value is also binary, p, n, okay. So using chi-square test, we're gonna decide whether these two variables, in this case attribute x and the class value, okay, whether these two variables are independent or not. So if the attribute x you selected, okay, if attribute x is independent of class value, okay, then there is no point of adding X here in this decision tree, right? Because X is independent of class value. That means X has nothing to do with class value. X is useless in determining class value, right? So that's the goal of chi-square test. So you form this table. So class value is P and X value is TF. So for each cell here, you this represents the number of data. So in this case, X value is T and its class value is P. Okay, the same thing for here. These are the number of data where X value is F and its class value is N. Okay, so you fill out all these values, all these counts, and do summation here. And just like we did in a previous slide, using this table, you can compute chi-square value. You can refer to the previous slide. Okay, so using this table, you can compute chi-square table, and if you look up the chi-square table, then you can decide whether these two variables are independent or not. Okay. So again, if it turns out that this X is independent of class value, then you simply ignore this, okay, and you stop here, okay. You simply put class label here. And if these two are dependent, okay, not independent, dependent, then you go ahead and add an X attribute here, okay, and keep going. Okay, that's the idea of chi-square test in pre-pruning. Earlier in this chapter, I said that people use post-pruning more often than pre-pruning. One of the reason is pre-pruning sometimes stops too early. So this slide shows the example of the problem. Pre-pruning stops too early. So let's take a look at this data. We have two attribute and the class attribute here. And suppose we use a chi-square test for pre-pruning. Then you select an attribute. So in this case, let's say you select attribute A, okay? Then you do chi-square test using attribute A and the class attribute, okay? But as you can see, attribute A is completely independent of class attribute here, because when attribute A is 0, class is 0, 1. When attribute A is 1, again class is 0, 1. Okay, so attribute A is completely independent of a class attribute. So if you select attribute A, okay, then if you use chi-square test, this is independent to class value. So this will be ignored. Okay. It's the same story if you choose attribute B. So if you choose attribute B, again, attribute B is completely independent of attribute class attribute, right? So if you use chi-square test, again, this is ignored. Okay, so you don't add this attribute to decision tree. So what actually happens in the end is the result of decision tree. Okay, the result of decision tree from this data by using chi-square pre-pruning is empty decision tree. So if you use this chi-square test, actually the result of this data, result of this decision tree is empty. So that's the problem. So sometimes, as I said, pre-pruning may stop the growth process too early, prematurely. Okay, so this is the one of the problem of pre-pruning. So no individual attribute shows any association with class value. Okay, because in this example, attribute A is independent to class value. Attribute B is again independent to class value. Okay. The problem is if you combine the value of attribute A and B together, now these combined values are dependent with class value. Okay. Each individual attributes are independent to class value, but the combined value of A and B, okay, combined value of A and B are dependent on class values. Okay, so that is the problem. So these are the problem of pre-pruning, and problem was it stops too early. But actually these kind of problems are very rare in practice, and one advantage of pre-pruning is pre-pruning is actually faster than post-pruning, so it has its own advantage too.